It's great to see so many of you. So thank you very much for joining us for our second New Frontiers talk of the academic year. So today it's my pleasure to introduce Sophie Koudmani. Sophie will be well known to many of you. She did her PhD here at the Institute of Astronomy with Deborah Sajaki and Martin Hainault, which she completed in 2021. After that, she was awarded a Junior Research Fellowship at St Catherine's College, which she held concurrently with a Flatiron Fellowship at the Centre for Computational Astrophysics in New York. She's currently an 1851 Royal Commission Fellow and Lecturer at the University of Hertfordshire, as well as retaining a non-stipendiary fellowship at St Catherine's College. So we have a lot of appointments, but it's great because it means we still get some of you. So Sophie's research focuses on modelling the formation and growth of massive black holes and their feedback in galaxy formation simulations. And today she's going to tell us about a multi-scale exploration of supermassive black holes in the multi-messenger era. Thanks very much, Sophie. Looking forward to your talk.
Thanks for the kind introduction, Anthony. And yeah, don't worry, the talk will not be as confusing as my affiliations, hopefully. Yeah, let's get straight into it. So first of all, let's start off with supermassive black holes in a nutshell. I'm sure many people here won't need this reminder, but let's recap the most important details. So first of all, virtually all large galaxies host a supermassive black hole at their center. And you can see this here in the sketch. So in the very nucleus of the galaxy, this is where the supermassive black hole sits. And this is also why, when the supermassive black hole is actively accreting gas, we often refer to it as an active galactic nucleus, or AGN for short. And you can see here in the zoom-in sketch, maybe this is broken down, but anyway, so you can see here in the zoom-in sketch, when it is in this active accretion phase, you get the accretion disk forming around the supermassive black hole, and this is what then gives off this massive amounts of energy in the form of radiation, winds, and jets. And this feedback is a crucial puzzle piece for understanding galaxy formation because it regulates the gas supply and thereby also regulates star formation. And some of this feedback also travels vast distances and then also becomes relevant for cosmology, which we can see here in this nice movie of the illustrious simulation. So you've got here in green the cosmic web, in blue you've got the galaxies, and then you can see these red hot explosions going off. And this is the active galactic nucleus feedback, the AGN feedback in action. And as you can see, this can affect even cosmological scales here if we look at the video again. And it really is a fantastic time to be studying these supermassive black holes. So to throw in the cliche, it's a golden age for supermassive black hole science. And this is because so many exciting facilities have just come online or are about to come online. So here's a brief overview. So this year we've got Rubin. Then in the late 2020s, we'll have Roman and SKA joining the effort. And then in the next decade, we can look forward to Athena, the next generation VLA, another radio telescope in the works, and of course, very excitingly, LISA. So we've recently had the first hints at gravitational waves from supermassive black holes via this putative detection of the gravitational wave background from supermassive black hole in spirals from pulsar timing arrays. But LISA will now be able to map individual supermassive black hole mergers. So LISA will be the space-borne gravitational wave interferometer. And there will also be other gravitational wave instruments that are being planned, for example, Einstein. And for all of these facilities, there will really be three key challenges. So first of all, the low surface brightness era. So you might have noticed how my supermassive black hole in a nutshell slide, I caveated things a bit with all large galaxies host a supermassive black hole at their center. But we're now increasingly also starting to push this towards the smaller galaxies, the so-called dwarf galaxies, and it seems that they might also be hosting massive black holes that also, again, go through active phases and contribute towards dwarf galaxy evolution. But instruments or facilities like Rubin and Roman are going to be able to tell us much more about this low surface brightness regime. And a similar but related challenge A different yet related challenge is the high-redshift era. So pushing towards the beginning of all of this, the infant supermassive black holes in the early universe, where JWST has already started giving us some hints of what that might look like. And then, of course, lastly, I already mentioned it, the multi-messenger era, so mapping supermassive black hole mergers across cosmic time. And at the heart of all of these challenges is understanding this co-evolution, so this interplay between black holes and their host galaxies across cosmic time. And what better tool to interpret this than cosmological simulations? So cosmological simulations are really at the heart of my research. And I first of all just want to briefly recap how these work. So with cosmological simulations, we model the cosmic evolution of a representative region of the universe. So this means we typically have box sizes between 30 and 300 megaparsecs. And these cosmological simulations are really important reference points for both galaxy and AGN surveys because these huge boxes allow you to model representative samples. And how do these work? So obviously you need the very basic physical processes that you code up for these simulations. So gravity and hydrodynamics, this is really what drives structure formation. But if you want to obtain realistic galaxies, there are a number of other key astrophysical processes that need to be included. So for example, gas cooling, star formation, stellar feedback. Central to this talk, black hole formation, accretion and feedback. And of course, other processes like magnetic fields, cosmic rays, and so forth. It's a long list that is certainly not finalized. And a lot of these processes are very hard also to resolve directly in the simulations. And this is especially true for what is the focus of today's talk, the supermassive black holes. So let's do a little thought experiment. If we really were to try to simulate supermassive black hole accretion and feedback ab initio, we would have to start at the event horizon. So for the supermassive black hole at the center of our Milky Way, this would mean scales of microparsecs. We would then need to model this accretion disk that I mentioned at the beginning that forms around the black hole, which is where all of the main feedback processes, such as the radiation, jets, and winds, originate. Then we're talking about scales of tens of milliparsecs. We then want to see how does this feedback couple in the central region of the galaxy, which is generally around tens of parsecs, and then drives these outflows that we saw in the video, which can reach scales of tens of kiloparsecs, if not larger. And then we want to see how these outflows interact with the cosmic web. So the cosmic gas inflows from the cosmic web, how are they triggered by mergers, and so on. And then we're talking about scales of tens of megaparsecs. So if you include all of this in a single simulation, you would need to span at the very least 14 orders of magnitude. And with current high-performance computing facilities, doing this across the whole cosmic time scale is completely infeasible and will remain so for the foreseeable future. So to model these processes, you need to come up with some tricks and do some compromises. So one of these would be idealized simulations, where you say, hey, let's just focus on a single galaxy here, and then resolve the processes in this galaxy extremely accurately. And there have been very impressive efforts where people are now managing for individual galaxies to span all the way from galaxy scales down to close to the event horizon. But of course, then you cannot get statistics for surveys, for example. So if you do want to have these statistics and also study the interaction with the cosmic environment, so you want to keep this whole box, then you have to make a different compromise, which is you say, okay, I do model here my representative cosmological region, but then everything that happens down here has to be encoded in a subgrid model. And this approach still remains hugely popular because it helps us to understand this co-evolution that I've been talking about. And there are really two key indicators from observations for this co-evolution that cosmological simulations have to help us understand. So the first is the scaling relations. So there are many scaling relations between galaxies and their supermassive black holes. I've given you one example here, which is between the black hole mass and the mass of the central bulge. So what this is telling us is that there is a relationship between the log of the black hole mass and the log of the central bulge, which we can see here in a kind of cartoonish way. And it spans actually across a huge range of masses, so from ellipticals down to disk galaxies. And actually one open question is, how low can we go with this relation? At what point do we simply no longer have a black hole? So this is where we're then starting to think about dwarf galaxies and the low surface brightness era. So the first challenge that I was mentioning. And another indicator towards this connection is, of course, the need for feedback. So if we think about the dark matter halo mass function, which is shown here in gray, and from simulations, and compare this with the galaxy stellar mass function that is observed and is shown here in black, we can see that both the low mass end and the high mass end of the galaxy stellar mass function are being suppressed. So in the kind of standard model of galaxy formation, it's then the assumption that the suppression of the low mass end is from supernova feedback. But at the high mass end, supernovae are definitely no longer powerful enough to drive out the gas, because we're talking about very deep potential wells here. And then you need something like AGN feedback to regulate this high mass end of the galaxy stellar mass function. However, as I mentioned, whether the low mass end is really just that simple is now starting to be called into question. And this takes us straight into the first challenge, which is active black holes and dwarf galaxies. So this is a field that has really grown in the past 10 years or so. And it all started off with a systematic analysis of SDSS by several different groups that started assembling the first large samples of active black holes and dwarf galaxies, so kind of in the hundreds. And they were really identified via their emission lines. So using a combination of the BPT diagram and also looking in particular for broad lines, which then allowed observers to estimate the masses. And since the systematic search of SDSS, this approach has only widened. So it's now really the AGN dwarf galaxies have been detected across many wavelengths, so also in the X-ray, radio, infrared. And crucially, we've also had high-resolution observations, which have allowed us to detect, for example, outflows in AGN-driven outflows in dwarf galaxies, and also to start establishing maybe some links between the strength of the AGN in the dwarf galaxies and star formation regulation. So this really activated the simulator. So we're like, okay, wow, this is really not how our standard model works for galaxy formation. So far, we've been trying to do it all with supernova feedback. Could we also try and integrate the AGN into this game and actually reproduce these relatively bright dwarf AGN that have been identified with SDSS? But there are a few challenges when one is trying to do that. So the first one is a strong supernova feedback. So the supernova feedback in the simulations is set up to be strong almost by definition, because it has to do this whole suppression of the galaxy stellar mass function that we saw earlier. But the problem is, if you have quite strong supernova feedback, then often it can evacuate all of the gas from the central region of the galaxy, which will then starve the black hole. So here we've got a plot from simulations of black hole mass versus stellar mass. And you can see here this growth path with the circles, that's AGN only, so without any supernova feedback integrated into the simulation. And then you can see the black hole can grow quite rapidly and also kind of in agreement with scaling relations. But as soon as you switch on supernova feedback, the growth here is completely stunted, because the supernova feedback is said to be quite strong. And the second problem with trying to get actually some active black holes in dwarf galaxies in simulation rather than just passive black holes are the offsets from the galaxy center. So in the dwarf galaxies, you have much shallower potential wells, which is also why the supernovae can be more successful there. But it also means that the black holes might start wandering in the simulations. And now the trouble with this wandering is that some of this, because of the shallow potential, might be physical, but some of it is also numerical, because it's very hard for simulations, again, going back to this resolution issue, to accurately resolve the dynamical friction that should migrate the black holes towards the center. So it's kind of unclear how much of the suppression because of the wandering in simulations should actually be happening. And the third one that I will also come back to is how black holes are generally grown in simulations. And this is using the Bondi formula. And for Bondi accretion, the black hole growth rate is directly proportional to the square of the black hole mass, which then makes it very difficult for the lighter black holes and dwarf galaxies to grow. So we decided to tackle this as a first kind of attempt to model these processes by just setting a constant Eddington fraction in our simulations that match the observed Eddington fractions. So you can see here X-ray luminosity versus black hole mass, and here some of these broad line detections where they estimated both the black hole mass via the broad line as well as the X-ray luminosity. And we essentially in the simulations just said as a first step, let's match these luminosities and see what an AGN like that would do to the system. And for that, we used the AREPO code. So AREPO is a so-called moving mesh code. So you've got this beautiful Voronoi mesh that you can see here behind me. And these are edge-on projections. So you're looking at the disk edge-on, and then you see the outflows coming out of the galaxy disk. And we tried two different injection techniques. So either isotropic thermal winds from the AGN, or you can see here these mass-loaded bipolar outflows. And here we've got a video of a subset of the simulation suite. So again, we've got edge on, but much more zoomed out now. And in the first row, you can see density projections. In the second row, temperature projections. And in the final row, you've got the vertical Z velocity. And in terms of interpreting these videos, the first column is relatively simple to interpret because it's the column without any feedback. So not much is happening. You can kind of just see the disk cooling down from the initial conditions. In the second column, we've got a simulation with only supernova feedback. So you can see the supernova feedback is able to drive large-scale outflows, but they're relatively cool and they're relatively slow. Whereas the next three columns are all different variants of supernova plus AGN feedback in that dwarf. And we can then see that with the added AGN feedback, the outflows are significantly faster and they're significantly hotter. However, when we analyze the impact of star formation in these systems, we found that actually the impact of the AGN was relatively minimal. And this is because the supermassive amount of energy that is being released actually just takes the path of least resistance and kind of just escapes perpendicularly to the disk. And because this is just an idealized simulation, so just a single galaxy, no cosmological environment, there are no cosmic gas inflows in the simulation. Because you could imagine that if there were, these powerful outflows would surely disrupt them, but there's nothing to disrupt here. So we then saw we really have to move towards a more comprehensive setup to analyze how these powerful AGN-driven outflows in dwarf galaxies might interact with their environment. So for these, we then took the Fable simulations to hand. So the Fable simulations are a cosmological simulation suite based on the ELASTO simulation, but with somewhat updated supernova and AGN feedback. And here in the projections, you can see the whole Fable simulation box at redshift 0 on the left-hand side and redshift 1 on the right-hand side. And all of the markers here show you the locations of AGN and low-mass galaxies. So this could turn into a bit of an eye test, but if you have a circle, that's a classical dwarf, triangle is a massive dwarf, and then the diamonds are M-star galaxies, so kind of Milky Way mass. And the color coding shows you how powerful the outflow is. But interestingly, for all of these three mass categories, we've then also zoomed into one representative galaxy and shown in these little insets the outflow structure at the virial radius. So we can see here in the dwarf regime, there can again be quite powerful outflows driven by these AGN. So this is really interesting. And in the early universe, these AGN are then also able to suppress star formation in Fable, just like we predicted might be happening. However, for the local dwarfs, these high luminosity AGN that were found by SDSS and other X-ray surveys as well are completely absent from Fable. And this is really due to the suppression of the black hole growth by the strong supernova feedback and also by Bondi. So you can kind of see this illustrated here. On the left-hand side, you've got the black hole mass, stellar mass scaling relations, and you can see here in the dwarf regime, the growth is really stunted and suppressed and kind of just hits that seeding floor at 10 to the 5. And we look at the AGN fraction dwarfs as a function of redshift. You can see here you've got these X-ray constraints in the local universe, but actually in this redshift range, there are no high luminosity X-ray AGN and dwarf galaxies whatsoever. So we found that the main culprit here, so it was partly the supernova feedback, but the main culprit here really was Bondi. So let's revisit a bit why Bondi is actually incorporated in these simulations in the first place. So you might recall from the beginning of the talk, the huge range of scales that is involved in supermassive black holes is obviously impossible to incorporate all at once. So the nice thing with Bondi is that it allows you to estimate the black hole mass growth rate by measuring gas properties around the scale of the Bondi radius, where you transition to this kind of freefall type solution. So you just have to measure the gas density and the sound speed at scales that are around 5 to 5,000 parsecs for supermassive black holes, which is already a lot better than the microparsecs that would be required if you were to go all the way down to the event horizon. But the problem with this Bondi solution is that there are lots of simplifying assumptions that don't necessarily apply in the galactic context. So, for example, spherical symmetry does not necessarily hold. So here on the left-hand side, you can see a typical Bondi flow, and on the right-hand side, you can see a flow pattern that might be more expected of a galaxy. So you've got rotation, which will break your spherical symmetry, the rotation of the disk, as well as outflows, which again will disrupt these assumptions. And of course, because of the strong dependency on the black hole mass, Bondi makes it very difficult to grow AGN and dwarfs or even just light seeds in the early universe. So what we then decided to do next is run so-called cosmological zoom-in simulations and consider variants of this fiducial Fable model, which is very representative of typical cosmological simulation setups. So for this, we ran high-resolution zoom-in simulation of dwarf galaxies with our repo. So the way that zoom-in simulations work is that you identify one galaxy in the box, and then you resolve that particular galaxy extremely well. So you essentially zoom in on it and put all of your resolution in that region of that galaxy of interest. And it then allows you to effectively sample through models, because it's obviously not nearly as expensive as zooming in on everything. And this is what we did here. So we considered, first of all, 2 supernova feedback setups. So the standard Fable calibration, where actually the supernova efficiency is set to 150%. So this is obviously optimistic at best. It's not necessarily unphysical to set it above 100%, because there are also other stellar feedback mechanisms, like, for example, stellar wind, that are not explicitly included in the Fable model. So this is the justification for setting it higher than 100 to say, oh, other energetic processes might be going on. But of course, you're also going to lose so much energy through the coupling. So yeah, 150% is very optimistic. And so we then set this to a more realistic supernova feedback parameterization of 50%, which is still fairly high, especially given the optimistic coupling that I just mentioned. And then we also explored 2 different strategies for growing the AGN that allow us to reach this high accretion parameter space. So one of them is increasing the boost factor alpha and the Bondi rate, which is essentially a free parameter that was originally designed to make up for the unresolved multi-phase nature of the ISM. But here we just use it as a cheap way of reaching that high accretion regime. And then we also try a gas supply limited accretion scheme, where we essentially just accrete as much gas as is available in the central region, limited by the Eddington rate. So here you've got a nice compact little table of all of our simulation runs. Of course, I do not expect you to read this, but what this illustrates is that we tested different accretion models, black hole seed masses, black hole seeding redshifts, AGN beauty cycles, and all of these different variations resulted in 3 distinct categories of outcomes for star formation suppression. So in some of them, the AGN is completely inefficient, doesn't do anything for star formation. Then we have some moderately efficient AGN that temporarily suppress star formation, or efficient AGN that actually completely quench the system. And we can see this here in the projections. So here you've got temperature maps of the dwarf galaxy. And then you also have the streamlines of the inflows and outflows. So inflows in blue, outflows in red. And this white circle here shows you the virial radius. And then you essentially have different snapshots across cosmic time. And here in the top row, we don't have any AGN in the simulation. So you can see, especially at early times, the cosmic gas inflows are quite strong, and it takes a while for the supernova feedback to build up and to be able to regulate this. With an AGN, you can drive efficient gas outflows that can regulate the cosmic gas inflows much earlier. And again, just like we saw with the previous work, these outflows are quite a bit hotter. But then once the AGN switches off, you can see at late times the cosmic gas inflows may get reestablished and star formation can then resume. But there's also a final, most catastrophic scenario where at late times the AGN still has some residual activity, which then allows it to maintain this hot bubble at the scale of the virial radius, so that the cosmic gas inflows are still prevented from reaching the galaxy, and in this case, the system remains quenched. We then also wanted to see whether there are any general signatures on the stellar populations in these dwarf galaxies, and whether this might allow us to rule out one model or another. Although broadly speaking, all of these models considered here are still within the observational constraints. So these observational constraints do not disfavor AGN feedback in dwarfs as an alternative to strong supernova feedback, but there are some signatures, so they tend to have more star formation suppression, be redder, and more metal poor. And one final thing for AGN and dwarf galaxies is the cusp versus core problem. So of course we can't conclude a discussion on dwarf galaxies without talking a little bit about these dwarf galaxy problems. So one of the most prominent dwarf galaxy problems is cusp versus core, which pertains to the shape of dwarf galaxy velocity, so rotation curves. So cold dark matter predicts a kind of fixed cuspy dark matter profile for a given halo mass. So you would expect relatively sharply rising rotation curves, as can be seen here by the black curve, which shows you dark matter only simulations. However, in observations, in some cases what you infer is actually slowly rising rotation curves, and this points towards more of a chord profile in the center. So this is where this cusp versus core debate comes from. And for a while, it seemed like that actually wasn't so much of an issue. So in addition to measurement uncertainties, a possible explanation is again just feedback that can create these cores via driving strong outflows and then driving potential fluctuations in the center. So there were then several simulation groups that actually demonstrated here, if I switch on my strong supernova feedback, which I happen to need anyway because I want to regulate star formation, then I can get something like this. But then a variant of the problem came onto the plan, which is the diversity of rotation curve problem, which is sometimes you have this core in the observations, this inferred core, I should say. Sometimes you appear to follow the predicted cusp profile quite well, but in other cases you might even be cuspier than NFW predictions. So there are many solutions to this. It might point towards the need towards alternative dark matter models, which is actively being explored by several groups. Again, it could also still be explained by the measurement uncertainties, which are significant, or of course baryonic feedback. So we were curious then whether introducing an AGN into the mix can explain this diversity. So if you have the interplay between all of the different processes. And for this, we use the FIRE simulation suite. So FIRE is a mainly zoom-in simulation suite, so zooming in on lots of different halos across the mass range. And because it has relatively bursty feedback implemented for the stellar feedback, it tends to mainly produce cores. So we wanted to see, can we get a broader distribution by also incorporating AGN? And I also mentioned earlier, cosmic rays are starting to become more of a consideration as well. So in some of the runs, we also incorporated cosmic rays to also study this interplay. And what we saw then in terms of dark matter density profiles, that if you do have this comprehensive dwarf model where you incorporate stellar feedback, AGN feedback, and also take into account cosmic rays, then indeed you are able to get this diversity of dwarf galaxy profiles. And we found that AGN actually play a dual role in cusp-to-core transformations. So sometimes the AGN is really powerful and also quite bursty. In this case, it can contribute to core formation or even make the core more pronounced. But in other cases, what also happens is that it actually just regulates star formation and thereby turns down this quite bursty stellar feedback and then actually preserves a cusp so that you're then also able to get a higher percentage of cusps within FIRE. And in terms of the black hole-driven core formation, so we considered a relatively small sample here within the study, but we had one where the AGN was quite clearly responsible for driving the core. And what was interesting then is that the core formation then correlates with a lower stellar mass to virial mass ratio. Whereas, of course, the prediction would be that higher stellar mass to virial mass ratios indicate cores if everything is stellar feedback driven. So actually, in this kind of region, there are no observations so far of cores with relatively low stellar mass to virial mass ratios. So it would be quite interesting actually to see whether, again, these can be uncovered with future surveys, for example, with Rubin, because at the moment it's just so difficult to disentangle these different things. So to measure rotation curves in a galaxy, for example, that also has an active black hole. In fact, this is how some of the first AGN-driven outflows were discovered in the first place for people who were trying to measure dwarf galaxy rotation curves and then had to throw some of them out because there was suddenly an unexpected, quite strong AGN-driven outflow, which made these measurements so difficult. Okay, but this is enough about AGN and dwarf galaxies. Let's move on to challenge 2. Which, again, I said is different yet related, so we haven't quite moved on. So let's now go from the low mass AGN that we've been discussing in the kind of local-ish universe to the infant supermassive black holes. So how did this all start? And interestingly, the whole search for these intermediate mass black holes, as we call them, in dwarf galaxies in the local universe, was originally often being motivated by this. Because people said, like, we know from the theoretical models, the black holes in dwarf galaxies, they cannot grow much. So if we find an intermediate mass black hole in a dwarf galaxy, it's likely a relic from the really early times. And we might be able to learn something about the seeds. But now that we know that there could actually be some AGN activity in the dwarf galaxies, it becomes a lot harder to motivate this argument, because the AGN activity may actually erase these early seeding signatures. So this then really gives us strong motivation to move to high redshift to investigate seeding. And we already investigated this high redshift population of AGN and low mass galaxies a bit with Fable. So you've got a plot with many panels. Maybe for now, let's just focus on the top row. So you've got here in the y-axis the Eddington ratio, and on the x-axis, you've got the black hole luminosity. So this then means that here in the upper right-hand corner, you've got black holes that are accreting efficiently and are quite bright. So again, in Fable, you can see, as we've now been discussing many times in the local universe, this corner is not very well occupied because it's so hard for the AGN and dwarf galaxies with the strong supernova feedback and Bondi to be accreting efficiently. But as we move to higher redshift, we can see how these supermassive black holes in dwarf galaxies are becoming more and more active. So the color coding here tells you the average stellar mass in the bin. So here the dark blue ones, this is kind of the dwarf galaxy regime. And indeed, there's a very high fraction in the so-called high-efficiency quasar mode at early times. And if we look at the bottom row, the color coding shows you the ratio between the black hole luminosity and the stellar luminosity. So in the purple regime, actually the black hole is just being heavily outshone by the stellar component. But in the green regime, the black hole is brighter than the stellar component. And again, we can see this is starting to look much more promising at high redshifts. And at the time, we're like, oh, new facilities might be able to probe this early phase. And excitingly, this is now exactly what is happening with JWST. So I'm sure everybody here has heard about this because so many of these exciting discoveries are happening right here at this institute. So the high redshift frontier and JWST has uncovered a myriad of active supermassive black holes in the early universe, many of them in low-mass galaxies. And so you can see this here in this plot where we've got black hole mass versus stellar mass, and these generally fall actually above the local relations. So the question now is, why is that? Is high redshift fundamentally different? Could it be completeness limits? But actually, regardless of what the answer to that question is, growing such overmassive black holes so early on is very, very difficult for models because of all of the same challenges that we were just talking about for the AGN and dwarf galaxies. And an exciting discovery recently here also at Cambridge by Ignace of a dormant overmassive black hole suggests that indeed completeness limits may not be the whole story. So it's not just that we're only discovering some kind of bright peak, now that we're also pushing towards more of a dormant population that is also overmassive, and again, very difficult to reproduce with the models, as can be seen here in this plot. So it kind of sits right at the top of the simulations. So it might be time now for us to revisit these fundamental assumptions that go into our cosmological models to be able to accurately capture and interpret these exciting high redshift observations. And supermassive black hole modeling in the majority of large volume cosmological simulations is really based on three key assumptions. So the first one we've already litigated. So black hole growth follows Bondi accretion, most of these. And the second one that is actually also quite relevant for the high redshift regime is that black hole growth is Eddington limited. So even if Bondi happens to have a very effective accretion episode, the simulation will just by definition cap it at Bondi and not at Eddington, and not allow it to go above that Eddington limit. So there is no scope for super Eddington accretion in the majority of cosmological simulations. And the third fundamental assumption for the high redshift universe is that in most cosmological simulations, black holes grow from massive seeds. This is almost a necessary assumption because of the first assumption, because with Bondi accretion, it is so difficult to grow light seeds, which is why most simulations assume this massive seed growth. And what we wanted to do now is to relax all three of these assumptions. So explore efficient accretion models in the low mass regime in large cosmological volumes, relax the Eddington limit, so allow it to go above Eddington if the gas supply allows, and also to investigate a wide range of seed masses, including light seeds. And of course, I've given you the references here. There are many other people who are now also following these approaches and relaxing these fundamental assumptions. So first of all, let's have a look how this impacts the black hole galaxy scaling relations. So here, for the fiducial accretion model in Fable, I've plotted black hole mass versus stellar mass, And the different color coding shows you now the different seed masses. So usually you would assume a 10 to the 5 seed mass, but we're now also testing 10 to the 4 in blue, 10 to the 3 in green, and 100 solar masses in orange. And the stars here show you these overmassive black holes from Maiolino and Harikane. And interestingly, with the standard fiducial Fable model, you might conclude, okay, it really looks like we need seeds of at least around 10 to the 4 if we want to get anything like this at early times. However, if you again increase the boost factor on the Bondi rate, so more efficient accretion, and you relax the accretion top limit to 10 times Eddington rather than Eddington, then you can see even with 10 to the 3 seeds, and in some cases there are also some little orange dots here from the 10 to the 2 very light seeds, you are able to reach this population at early times. So with enhanced Bondi and a relaxed Eddington limit, light seeds may also grow overmassive in the very early universe. Now the next question though is, would we be able to see any of this? So how bright are these objects? So first of all, let's consider again the simulated and the observed population in the bolometric luminosity black hole mass space. This is again here for the fiducial model, and then you can see for all of the seed masses, the observations indeed at the moment are at the very top of the simulated distribution. So we do have a bit of a kind of tip of the iceberg scenario with a lot of these. They are indeed very, very bright compared to the simulated black holes. And this is also true if we boost the accretion and relax the Eddington limit. Then we're still talking about relatively bright objects, although of course there's now more overlap. So this then motivated us to do a bit more of a completeness analysis. So this is very much in prep, and I look forward to receiving feedback on this. I've already received some. But here there's just a relatively generous, blunt luminosity cut now in the plot of 10 to the 42 ergs per second. And I've separated out the light seeds of 100 and 1,000 here in the left panel, and the heavy seeds of 10 to the 4 and 10 to the 5. And with this luminosity cut, so you're only including the bright black holes in the scaling relations, you can see with the heavy seeds, there's almost a perfect overlap now actually between the observed populations and the simulated supermassive black hole populations. Whereas with the light seeds, of course, you're not going to get anything like this. So you could walk away from this and say like, this proves it, I always knew it. Heavy seeds are the solution to all of our questions. But of course, if you consider the boosted variant, then you can see that even with the light seeds, you are able to reproduce this population. So now the question is, how are we going to distinguish between the scenarios of super Eddington plus light seeds or massive seeds plus more moderate growth? So one interesting signature, of course, is that we can see there are some more kind of undermassive black holes in this plot here on the left-hand side with the light seeds. So currently, most of the observations are limited around black hole masses of 10 to the 6, but with future surveys that even only need to push down to something like 10 to the 5, if these do uncover these undermassive black holes, it could, of course, with the caveat of all of these modeling uncertainties, point towards a light seed population. But of course, what we really want to do is reduce these modeling uncertainties, so move away from Bondi. It kind of becomes a bit unsatisfactory to just keep playing around with the boost factor and see what happens and how we can we reproduce it. We want to move kind of more towards first principles, supermassive black hole accretion and feedback, so really move beyond Bondi. And there have been some exciting approaches here. So one is torque-based accretion, and the other one is the accretion disk particle method. So with the accretion disk particle method, you don't just model the black hole particle with its mass in the simulation, but the black hole particle now also tracks the properties of the unresolved accretion disk surrounding the black hole. And then you're now keeping track of 4 variables, so black hole mass, black hole spin, disk mass, and disk angular momentum. And of course, self-consistently tracking the black hole spin is very exciting because it then also allows you to self-consistently calculate things like the radiative efficiency and the jet power. But for this to work, you really need to measure the mass and angular momentum inflows at the scale of the outer accretion disk directly from the hydrosolver and then feed that into the model. And the black hole mass and spin evolution then proceeds with the subgrid model. So there are lots of equations, and I'd recommend that if you want to see them in detail, you consult my 2024 paper. But I'm now just going to give an example of kind of the structure of how this works for the mass flows, which are not as complicated as the angular momentum. But essentially, for tracking the disk mass and the black hole mass, the disk mass change, it's just that it decreases because of accretion onto the black hole, and it increases because of the inflows from the environment. And then the black hole mass increases because of accretion corrected for by the radiative efficiency. Now, the inflows from the environment, as I said, you measure directly from the hydrosolver, and the accretion rates and the radiative efficiency you generally, with these types of models, get from an analytical disk model, which is then always the Shakur-Zunyaev-thin alpha disk, because it's the only accretion disk model that has a global analytical solution. So this is why thus far most of these efforts have been focused on modeling thin disks. But of course the issue is that this thin disk model doesn't always apply, especially if you go to lower Eddington rates. As the density drops, radiative cooling also gets less and less efficient, and then the accretion flow becomes very hot and starts to puff up. So you get this thick disk, and it's likely a kind of continuous transition where this hot flow starts going in the center and then expands. And there are also observational hints that this is indeed how this transition proceeds between these two types of accretion flows. So what we then wanted to do is to create the so-called unified accretion disk particle method that is able to switch between different accretion disk states so that it can be implemented and applied for all radiative regimes. Of course, the keen eye might notice that there is another regime here above the thin disk, the super Eddington. This is currently not incorporated, but in the works, and happy to talk about it later. But for now, this really is already quite complicated. And I told you that the only global analytical solution is available for the thin disk, so you might have the very justified question of how these other disk states work. So this is really a combination of different ingredients. So first of all, we still use self-similar analytical solutions for the so-called ADAF theory. So ADAF just stands for advection-dominated accretion flow, and ADIOS is then the variant that explicitly includes the modeling of the outflows from the accretion disk. So the self-similar theory, unfortunately, because it's self-similar, breaks down at the boundaries, so crucially at the innermost stable circular orbit, which is where a lot of the feedback originates from. So stuff like the radiative efficiency, which is measured at the innermost stable circular orbit, we then directly take from GR MHD simulations, so general relativistic radiation magnetohydrodynamic simulations, and essentially couple this to the self-similar theory. And there are a few other quantities that are also measured at this innermost stable circular orbit. For example, the spin-up function for modeling the black hole spin, and also the disk precession. So again, we then directly take this from these very high-resolution disk simulations. How much time do I have left?
5 minutes.
Okay, so I'm going to use 5 minutes to very briefly give you a flavor of challenge 3 that I mentioned, supermassive black hole binaries. So here you can see a sketch kind of the life cycle of supermassive black hole binaries. So you've got the galaxies merging, their supermassive black holes sinking to the center, starting to orbit each other and form a binary. And then, of course, eventually they coalesce, and you've got this gravitational wave emission. And interestingly, this kind of intermediate phase, the white binary phase, should already be in the reach of next generation radio facilities in terms of resolving these binaries directly. There are already some VLBI detections. So we then wanted to apply our unified accretion disk model to make predictions for these type of wide binaries. So for this, we investigated two setups. So first of all, the vanilla setup, where you have two equal mass binaries that are aligned with this outer second binary disk, or a slightly more interesting setup, where you've got a mass ratio of 1:3 for the two supermassive black holes, and they're misaligned from the outer disk, so you get slightly more chaotic inflow patterns. And for these, we then wanted to make detectability predictions for different accretion disk models. So here in the top row, let's focus on the vanilla binary first. So here primary and secondary are plotted together because it's essentially the same thing because of the symmetry of the problem. So here in the top row, you've got the X-ray luminosity, and the dark purple solid line shows you the prediction for a thin disk only model. And then you can see you get a quite bright X-ray counterpart towards this binary. But if you use the unified model, then we actually find that the accretion rates are not high enough to be in the thin disk state. Instead, you're in this combined truncated state. And then the X-ray luminosities are quite a bit lower because the radiative efficiency is so much lower with this model. However, jet production for these thick disks often tends to be more efficient. So while they are much less X-ray bright, they might be much stronger in the radio. So you get actually completely different electromagnetic counterpart predictions. The same applies here for the second setup. And then the last thing that I want to mention for the binaries is the Lense-Tearing precession. So this is a precession effect that occurs when the angular momentum vector of the accretion disk and the black hole spin are misaligned. And how this then realignment happens and the torques act depends on the accretion disk type that you've got. So for thin disks, you have this Bardeen-Patterson effect, where essentially only the inner part of the disk is slowly realigned, and this happens mainly through viscosity. Whereas with the thick disk, the whole flow is so strongly coupled by pressure waves that actually, in many cases, the sound crossing timescale will be shorter than the precession timescale, and the effect is that this whole inner hot flow precesses as a solid body. So you can then get quite strong precession effects with this model. So here I've got kind of plots of these versors. So the versors are essentially just unit vectors of the angular momentum. So both here for the black hole versor and the disk versor. And in the top row, we've got the thin disk only model, so you just get slow realignment. Whereas in the bottom row with the unified model, you get this very significant precession, which again may be A, detectable, and B, will significantly change the impact of feedback, because you then will also have more distributed feedback as the direction of the jet is coupled to the direction of the spin. Okay, this then takes me to my conclusion slide. So today I've talked to you about new supermassive black hole modeling approaches for the low surface brightness, high redshift, and multi-messenger era. And yeah, AGM may play a significant role in the evolution of low-mass galaxies, especially at high redshift. And we also talked about new modeling approaches for incorporating accretion disk physics into these simulations. And then we discussed how the electromagnetic signatures, as well as the spin evolution, are hugely sensitive to this. So my final minute, I would just say, where to next? So, of course, the next thing is to include all of these new physics models, in particular the accretion disk particle method, with accurate seeding mechanisms and dynamics, and then run cosmological zoom-in simulations with this. So this is actually ongoing work within this new AREPO Renaissance project, as well as some other local collaborations here in Cambridge. And then we also really want to, of course, incorporate these accretion disk models in large cosmological volumes to make these JWST predictions even more accurate that I was talking about. But for this, we really need to think about a coarse-grained version, and this is currently in development with Learning the Universe, and again also with local collaborators. Yeah, thank you.